Hello students, this is the sixth episode on alcohol, phenols and ether. Today we will be focusing more on the physical and chemical properties of phenol. Though there are just three important physical properties, but a good number of chemical properties are awaiting in this chapter. Lots of chemical equations and relations give this chapter a unique nature. So let us study vividly the first with the physical properties of phenol. The physical properties. You may see the first point stating that pure phenols are colorless liquids or colorless solids, but sometimes they turn reddish due to the atmospheric oxidation. And if there are the presence of NO2 group, the nitro group in phenols, it will impart the yellow color. So student, here we can understand that the pure phenols are colorless solids or liquid, but if there are impurities like nitro group, they will impart yellow color, and if it get oxygen inside, that means if it get oxidized, it may turn reddish. The second point illustrates that the presence of the OH group makes phenol that should be soluble in water, but it is actually not. Phenols are not soluble in water. We have already learned that the alcohols are highly soluble because they have the OH group. But in the same time, you can see that there is a bulky nonpolar aryl group, that is C6H5, a bulky one, a very weighty one, and is a nonpolar aryl group which dominates over the OH group, and hence though there is the presence of OH group in phenol, but they are not soluble in water. The third point illustrates about the para-isomers and the ortho-isomers. Para-isomers is highly associated due to intermolecular hydrogen bonding, but ortho-isomers exist as monomer due to intramolecular hydrogen bonding and is steam volatile. So you know that this is the way by which you can use to separate the para-isomers with the ortho-isomers. Now, if we just go to the chemical properties of phenol, there are a lot of properties. The first point I would like to illustrate is about the acidic property of phenol. You can see here the first equation stating that when we are treating with sodium in the presence of ether, phenol reacts with sodium to produce the hydrogen gas, and this is the acidic nature. But you know that phenols are weaker acid, even more than that of the carboxylic acid. It is a very weak acid and it does not decompose carbonates or bicarbonates. Usually we have seen the acids react with carbonates and bicarbonates to produce carbon dioxide and water. But phenol can't do it. Why? Because they are weak acid. Phenols are stronger acids than alcohol and water. They turn blue litmus red. But alcohols can't turn blue litmus red. What is the reason behind? The reason is very simple. This is because of the resonance. The oxygen atom of the OH group acquires partial positive charge. Due to the partial positive charge on oxygen, it attracts the bond pair of electron towards itself. Yes, because of the positive charge on oxygen, it attracts the bond pair because oxygen and hydrogen is with a bond pair of electron that is being pulled towards oxygen. So it attracts the bond pair of electron itself, making the release of proton easier. So hydrogen would be losing that very electron of itself because oxygen pulls that electron of that hydrogen towards itself, and hydrogen can be eloped. Hydrogen can be removed, and any factor which stabilizes the phenoxide ion will increase the acid strength of phenol. In the second point, you can see about the electro-releasing group like the alkyl group, like the amine group NH2, it intensifies the negative charge on oxygen atom and makes phenoxide ion less stable. So we should have an intention of making or intensifying the positive charge on the oxygen atom. But when it becomes negative, it becomes less stable. Let us see for the next point about the electro-withdrawing group. That is all the halogens, the cyano, the nitro. These type are of this type of functional groups are called as the electro-withdrawing groups, and they have minus I effect and minus R effect. Both the effects are present on this type of compounds, and they disperse the negative charge and make phenoxide ion more stable. Acid strength increases with the increase in the number of the electron withdrawing groups. And here I have given you a relation between the acidic strength. By the increasing of the acidic strength, you can see para-nitrophenol has more the acidic strength with respect to the orthonitrophenol, and orthonitrophenol is more acidic than the metanitrophenol, and metanitrophenol is much more acidic than that of phenol. So with the para-nitro group, it intensifies the acidic strength. Let us go to the other point about the halophenols. So yes, student, in case of the halophenols, halogens has minus I and plus R effect, but minus I predominates. All halophenols, that is except the parafluorophenols, are more acidic than phenol. And if you go down the series of the halogens right from chlorine to iodine, you would see the acidity decreases. It is all because due to the decrease in the minus I effect of the halogen. If you go finally on the acidic property of phenol, the last point illustrates about the plus I effect of the alkyl groups. Because the alkyl groups are the electron donating groups, and due to their hyperconjugation effect, what it happens, like all cresols are weaker acids than phenol. Since hyperconjugative effect cannot operate at the meta position and thus make metacresol more acidic than orthocresol. So this usually comes a question in your question papers saying why metacresol. Student, you please see the last line saying that why metacresol are more acidic than the orthocresol. You will just say all cresols are weaker than phenols, but since they have hyperconjugate effect not operated on meta position, so metacresols are more acidic than the orthocresol. I have something more to say, the difference between the alcohols and phenol. Before I go to the board and illustrate more on the chemical properties, I would ask the student to go with the difference between the alcohols and phenol. So the first point is about the litmus paper. If you have the blue litmus, with alcohols it will remain no effect, but with phenols it will turn the blue litmus red. Now the second one, neutral ferric chloride solution. The neutral ferric chloride solution has no effect on alcohols, but in phenol it gives different colors, sometimes violet, blue, green, etc. All these color differ because we take different kind of the phenols and its derivatives like cresol, resorcinol, catechol. So they are all the derivatives of phenol. So other derivatives of phenol would show different colors with neutral ferric chloride solution. Our third point to illustrate is about the bromine water. Students, you know the bromine water is red in color, And now with alcohols, it will remain no effect. But with phenols, it would give a white precipitate. So this is another more indication by which you can understand the difference between alcohols and phenol. The fourth point is the Lieberman's test. Lieberman's test with alcohols will have no effect, but with phenols it gives a red color when warmed with sodium nitrite. I repeat, it gives red color when warmed with sodium nitrite. And finally, to go with the coupling reactions, and that is, this alcohol will have no effect on that, but phenols, they would give a different colored dye, sometimes yellow or orange, red, etc., with the ice cold solution of benzene diazonium chloride. I would ask the student to take a screenshot of this matter, and then we would be going directly to the board to illustrate more on the chemical properties of the phenol. So in the chemical properties of phenol, we have seen about the acidic nature of phenol. The second thing what you are going to see is here, when phenol is allowed to react with zinc dust. So when it is allowed to react with zinc dust and undergoes distillation process, we get benzene, and together with that we get the zinc oxide. So you can just understand the zinc get oxidized and benzene on the other hand get reduced. We can also use acetyl chloride with phenol. In the place of with it, we have to react it with pyridine or sodium hydroxide. We get here phenyl acetate and hydrochloric acid. So phenyl acetate and hydrochloric acid, when we treat phenol with any acetyl chloride in the presence of pyridine or sodium hydroxide. If you use here acetic anhydride, with phenol, you can see phenyl acetate, together with it you get here acetic acid. And point number 5 speaks, similarly when we are using benzyl chloride together with phenol, we also get phenyl acetate, PHENYL, phenyl acetate, and together with it we get hydrochloric acid. These are almost similar. Now on the 6th point, we can see if we treat with phosphorus pentachloride, you get your chlorobenzene, together with that hydrochloric acid and POCl3. So PCl5 reacts with it to form chlorobenzene. Similarly, PCl3 won't react. On the 7th point, here this is a very important reaction, because it is shown by particularly phenol, which have got the enolic group. What is the enolic group? I have written here all compounds with double bond COH. So whoever have this double bond C and OH, this is what we call as the enolic group. And this compound, whoever have the enolic group, react with FeCl3 solution. It will react with FeCl3 solution to give a complex ion which will be either violet, blue, green, or even red in color. So this is an indication. So if you give alcohols they never react with FeCl3. But phenols react with neutral ferric chloride solution to give a red, violet, blue or green in color solution. Next point, we have to go with 8. That is, whenever you react phenol with bromine water, that means bromine is dissolved in water, and if you treat with phenol, you can see here forming tribromophenol. So 2,4,6 tribromophenol together with hydroboric acid. So here you can see tribromophenol is being formed. So phenol reacts with bromine to give tribromophenol. Similarly, if we are not using the aqueous, directly bromine liquid, if you just give it in the presence of carbon disulfide at a temperature around the room temperature or 293 Kelvin, we can get either the bromine in the ortho position or the para position. So this is 2-bromophenol or 4-bromophenol. Remember, this para or 4-bromophenol is a major compound in this process. So student, on the 10th point, let us see if we take phenol here. If we take phenol here and put concentrated nitric acid, we are going to get trinitrophenol, what we usually call it as picric acid. But at the same time, if we use dilute nitric acid, you are going to get the paranitrophenol, which is around 79%, with just 19% you will be having the orthonitrophenol. So this is a major part, that is paranitrophenol is being formed as a major product when dilute nitric acid is treated with phenol. But if concentrated nitric acid is used, we have picric acid instead. On point 11, we have to discuss with concentrated sulfuric acid at 373 Kelvin, and we have to heat it for a prolonged time. You just cannot just heat it and leave the thing. So when you heat it for a prolonged time, you can get the sulfuric part on the ortho and the para position of the phenol. And then when you treat with nitric acid, concentrated nitric acid, you again get the picric acid. So student, you can get this picric acid once again because it substitutes out the sulfuric group with the nitric acid, with the nitro group. On point number 12, we have something different, that is, we are giving out the nitrous acid. How we are going to make nitrous acid, we cannot get in the market. So we treat with NaNO2 and HCl. When sodium nitrite is treated with HCl at a temperature between 0 to 5 degrees centigrade, you get your HNO2, and this HNO2 reacts with phenol to form para-nitrosophenol. What I told? Para-nitrosophenol. This para-nitrosophenol reacts with dilute nitric acid to give para-nitrophenol. So para-nitrosophenol will react with dilute nitric acid to give para-nitrophenol. On point number 13, we have to discuss here like this. When we have a phenol attached to the sulfonic group and wants to get it from the phenol, we have to give it a temperature of 373 Kelvin. So phenol, when you give concentrated sulfuric acid at a temperature of 373 Kelvin, we are going to get the sulfonic group on the para position. But if you give a temperature of 298 Kelvin, we get it in the ortho position. Now you might again ask me, 373, why it is not showing both the compound in the ortho and the para? Because this has to be heated for a prolonged time. And when you just heat it at just a temperature of 373 without giving a prolonged time heating, so it is going to form the sulfonic group at the para position, while at 298 Kelvin, just the room temperature, it is going to give at the ortho position. We have to discuss it on the Friedel-Crafts reaction. Friedel-Crafts reaction says that when phenol reacts with, like here, acetyl chloride, and this is alkyl chloride. So alkylation and acylation. So alkylation and acylation is very important for Friedel-Crafts reaction. In the presence of anhydrous aluminum chloride, you can see this H reacts with the Cl to form HCl. So what is left over? This CH3 get attached with OCH3, and it forms this OH forms this H forms with Cl. This H will take the Cl and O, and it forms here OH, and it forms OH and CH3 and OH and CH. So you can see in the meta group and the ortho group, you can see the the cresol get the cresol here at the ortho position and the para position together with the hydrogen chloride. Similarly, with the acyl chloride acylation, you can see this COCH3 get attached here because they remove the hydrogen from this place. So this hydrogen remains here. The hydrogen from here, it goes with the Cl and it forms HCl. Similarly, this H takes this Cl and forms HCl. And what is remaining here is COCH3 get attached to the ortho or the para position. If the hydrogen is removed from here, you get here the ortho. If it is still removed from the para position, it is called as the para path. Now, if we go for the cold-base reaction, you can see phenol with sodium hydroxide. We get here sodium phenoxide. And sodium phenoxide, in treating with carbon dioxide at a temperature of 400 Kelvin, between 4 to 7 atmosphere, we get a compound with OCOONA, which on treating with hydrochloric acid and water produce salicylic acid. So student, here we have completed how we have to get salicylic acid from phenol. And now for the formation of aspirin. I have already told you this is salicylic acid. Salicylic acid, when we treat with acetyl anhydride, in the presence of constant sulfuric acid, it is going to make 2-acetobenzoic acid. So 2-acetobenzoic acid, this is 1, this is 2, 2-acetobenzoic acid, which we call this as aspirin. So this is a pain reliever, as well as if there is a major heart attack, we have to give it in the form of a sedative as an SOS to the patient who are having heart attacks before we take them to the doctors. So this is aspirin. This is very important medicine. We have an important drug in the market. So this we are getting it from the salicylic acid. When we are taking acetic anhydride in the presence of constant sulfuric acid, we get aspirin. Together with it, we get acetic acid. You know, like acetic acid is used as vinegar with 40% acetic acid. In tribally, we are selling it in the form of vinegar. Next, here you see again, if you take salicylic acid and treat with phenol and reflux it with hydrochloric acid, we get wintergreen constituent. I know that you already know about this wintergreen. It is just like iodex. If there is any kind of pain in muscle, we just smear iodex or any kind of thing like that which release the pain. So student, this is really a working thing. That is, it produces the material which is used as a constituent in the wintergreen lotion. In going with the Raymond-Timan reaction, phenol, when it is treated with chloroform in the presence of NaOH or KOH and then treated with NaOH followed by HCl, it produces here salicylaldehyde, SALICYALDEHYDE. So remember, when you are using chloroform and if you substitute chloroform with carbon tetrachloride, when you are substituting chloroform with carbon tetrachloride, you can see you are getting here salicylic acid. This is salicylic acid, salicylic acid, ACID, salicylic acid. So this is a major important thing, that when you are using chloroform, you are getting here salicylaldehyde, while if you use here carbon tetrachloride, you are getting here salicylic acid. On the point number 19, here is very important that when you pass hydrogen in the presence of nickel at a temperature around 530 Kelvin, we get here cyclohexanol. So directly from the aromatic, you can get aliphatic only by this process. So student, be careful. Point number 19 is very important. From the aromatic, if we ask you to find the aliphatic part, hydrogen works a lot, where in the presence of nickel at 530 Kelvin, it produces cyclohexanol. And finally you can see on question point number 20 that phenol, when it reacts with hydrogen in the presence of molybdenum oxide, and when it is heated in the presence of molybdenum oxide, it goes to form benzene. And this is phthalic anhydride. So phthalic, T-H-A-L-I-C, phthalic anhydride. And this phthalic anhydride, when it is allowed to react with phenol, 2 moles of phenol, what happens? A molecule of water gets out. A molecule of water gets out, and you get here a compound with the phthalic part together being joined with 2 phenol. It joins with phenol, and this we are using readily in our chemistry lab. Can anybody tell me here what's the name? Just think, this is phthalic anhydride. When you are reacting with phenol, we are getting here phenolphthalein, Phenol, Phthalene, phenolphthalein. So student, be careful when we ask for making of the phenolphthalein. You have to take the phthalic anhydride with 2 moles of phenol in the presence of sulfuric acid. In the presence of sulfuric acid, it produces phenolphthalein. And finally, we have now the difference between the alcohols and phenol. So student, get ready. You have to know about how phenols and alcohols can be differentiated. Point number 1, with the blue litmus paper, it turns red for phenol. For alcohols, no effect. For neutral ferric chloride solution, alcohols, you can see there is no effect on it, but it gives different colors with phenol, like violet, like blue, green, etc. If we treat with the bromine water, alcohols will have no effect, but phenols give a white precipitate. With Lieberman's test, that is point number 4, alcohols will have no effect, but in case of phenols, it will give you a red color when warmed with sodium nitride. So student, when we treat Lieberman test with phenol, it gives you a red color which when warmed with sodium nitride. And finally, coupling reaction which is coming forward is with alcohol, no effect, but with phenols it gives a color dye, either yellow, orange, red, etc. when treated at ice cold solution of N2Cl of benzene, that is benzene diazonium chloride. So student, point number 5 and point number 4 is very important, the coupling reaction and Lieberman's test. Particularly the coupling reaction, it gives a different color with phenols, and this is important. And so finally we have come to the end of this phenol. Hopefully you have understood it. If there is any confusion, let me know at the earliest. Till then, goodbye.